Hello everyone. Now we are in the second week. What we're looking at this week is basically to look at graphs and to look at various algorithms that we can use for test case design using graphs. In the last module, I gave you a brief background of graphs as it was necessary for this course. So to recap what we saw in the last module, we saw what graphs were and basic concepts like degree of a vertex, what is the notion of a path, and what are trips, what is visiting a node, and a few other details, right? So the plan is to be able to use graphs to design test cases. So we'll take software artifacts like code, requirement, design, model them as graphs, and see how to design test cases, how to define coverage criteria, and then to design test cases using graphs. So we'll first, in the first two modules that we will see as a part of graph-based testing, what I'll do is we'll look at coverage criteria purely based on graphs. I will not really show you too many examples of how software artifacts are modeled as graphs. Instead, we'll directly deal with graphs as data structures and define coverage criteria. Right? In today's lecture, we'll define coverage criteria that are based on the structure of a graph, that are based on nodes, vertices, edges, paths, and so on. The next lecture, I'll look at some algorithms that deal with coverage criteria that are again based on the structure of the graph. Moving on, what we'll do is we'll annotate the graph, the vertices and the edges of the graph with statements and other entities, and we'll define coverage criteria based on data that deals within the graph, right? After we do these three kinds of coverage criteria, look at how they are related to each other and how they can be used to design test cases based on graphs, we will consider a later module where we will take various kinds of software artifacts. We'll begin with code, then go on to design, then move on to requirements, model each of them as graphs, and then see how the coverage criteria that we will be learning throughout these modules can be used to actually design test cases for covering these software artifacts. So what will we be doing at? So first, today's module, I'll deal with structural coverage criteria. In the next module also, we'll look at structural coverage criteria, but we'll focus on algorithms. And then we will look at what is called data flow coverage criteria, which consider graphs with data, variables and their values, and then define coverage based on them. As I told you, post this, we'll take several software artifacts one at a time, model them as graphs, and see how to use these coverage criteria to design test cases. So we begin with coverage criteria in this course. Right, so what are the various coverage criteria that we are going to see? Here is a listing. So we'll begin with what is called node coverage or vertex coverage. We'll define a test requirement which says you have to visit every node, right? And then we'll define test coverage requirements for edge coverage, where we say you visit every edge. Then we look at edge pair coverage, which insists on visiting every consecutive pairs of edges, which are paths of length 2. Then we look at path coverage in the graph. In path coverage, these are the various things that we look at. We look at complete path coverage, which may not be feasible all the time. Then we'll move on and look at a very popular coverage criteria called prime path coverage. And then to make prime path coverage feasible, we'll look at these round trip coverage criteria, right? So we'll see each of these one at a time. So we begin with node coverage. What is node coverage? It simply insists that you have a set of test cases that visit every node in your graph, right? So it could be the case that the graph corresponding to a particular software artifact can be connected or disconnected. If it's disconnected, then the graph has several disjoint components. What do we mean by disjoint components? There are no edges between vertices of these components. So in which case, if I say node coverage needs to visit every node, you might ask, how do I go and visit other nodes in the graph, right? So what we insist is that node coverage visits every reachable node. Every reachable node means every node that can be reached from the designated initial node, right? So what we mean is that per reachable component that is connected, you visit every node. So what is node coverage? Node coverage says, the test requirement for node coverage, abbreviated as TR, says you basically write a set of test cases that will visit each node in the graph. Now, how will you write a set of test cases that will visit each node in the graph? What will a test case look like? How can you go about visiting nodes in a graph? You have to start from the initial state and you have to walk along paths in the graph. As you walk along paths, you visit various different nodes, right? So, a set of test cases that will meet the test requirement of node coverage would be a set of test paths that begin at an initial state and visit every reachable node in the graph. I'll show you an example after a couple of slides. And then the next coverage criteria that we will be looking at, it was what is called edge coverage. So like node coverage, edge coverage basically insists that you visit every edge in the graph, right? So your test requirement says you visit each reachable path of length up to 1. Right? So you might ask, when I said visit every edge, why am I writing it as visit each reachable path of length up to 1? Now look at an edge in a graph. What does an edge look like? An edge can be thought of as a path of length 1, right? Because it just connects two vertices. But instead of saying visit every path of length 1, which basically means visit every edge, we are slightly modifying the condition to say visit every path of length up to 1, which means you visit paths of length 0 and paths of length 1. What do paths of length 0 correspond to? Paths of length 0 correspond to paths that just contain a single vertex, right? We want to be able to say that edge coverage subsumes node coverage, in the sense that if I have a set of test paths that satisfy edge coverage, then those set of test paths will also satisfy node coverage. Because we want to be able to say so, we modify edge coverage criteria definition to include that it visits every path of length up to 1. So it visits every single vertex and it visits every single edge. So by definition, edge coverage will subsume node coverage. Here is an example to illustrate how edge and node coverage works. So here is a small 3 vertex graph. Vertex 1 is the initial vertex, as you can see, it's marked with this incoming arrow. Vertex 3 is the final vertex, it's marked with this double circle, and it's a small graph. If you remember in the previous example, we had an if statement and I showed you how to model the control flow graph corresponding to that if statement, remember, which didn't have an else part, it just had the then part. This was the graph that correspond to the control flow graph of that if statement. I've of course removed the labels and the edges and all that stuff because we are looking at purely structural coverage criteria, which defines coverage criteria based on the basic structure of the graph. Doesn't really look at labels of edges or vertices, right? So in this graph, what would be node and edge coverage? Node coverage, the test requirement for node coverage says that there are 3 nodes. So you please visit all 3 reachable nodes. All 3 of them are reachable here, right? So how many paths can visit all 3 reachable nodes? So I could take this path, I start from 1, I go to 2 and then to 3, right? In this path, I have visited all the 3 nodes, 1, 2 and 3. There is another possible path in the graph. I could start from 1 and then I go to 3. Suppose I take this as the test path corresponding to the test requirement, then I have only partially achieved node coverage. I have visited the nodes 1 and 3. I have not visited the nodes 2. There's no harm in choosing that. Suppose you choose that, then you have to add this path also, 1, 2 and 3. But instead, I could directly choose this path 1, 2 and 3 as my test path, and in that case, I would have directly met the test requirement of node coverage with just one path, right? Now, let's look at edge coverage. How many edges are there in the graph? There are 3 edges in the graph. One edge from 1 to 2, one edge from 1 to 3, and another edge from 2 to 3. What does edge coverage mean? The test requirement or TR for edge coverage says you visit all the 3 edges, the edge 1, 2, the edge 1, 3 and the edge 2, 3, right? Here, if you see, suppose I take this path 1, 2 and 3. How many edges do I visit in this path? I visit 1, 2 and 2, 3. So I visited 2 edges. So that is this path here. But I have to be able to visit the edge 1, 3. So I have to take this path. So to meet the test requirement for edge coverage in this graph, I need 2 test paths. The test path 1, 2, 3 and then the test path 1, 3, right? So yeah, this is another small observation. Suppose the graph is a sort of a straight line, right? There are no branching, and it just corresponds to some code that corresponds to a sequence of statements. It's just like one linear order or a straight line or a chain, right? In that case, node and edge coverage are the same, because when I visit every edge, there's only one path in the graph. I visited the path, and in that process, I visited every node also. So node and edge coverage become different in terms of the test paths that satisfy it only if there is a branching in the graph, right? So we move on. What is the next coverage criteria that was there in my list? I'll go back to that slide. Yeah, so we did node coverage, which basically says visit every node. So you write test paths that visit every node. Edge coverage says visit every edge once. So you write test paths that visit every edge. Now we'll move on to edge pair coverage and then look at path coverage. Before we move on to edge pair coverage, I would like you to spend a minute thinking about what would node coverage, how would node coverage and edge coverage be useful. Assuming that such a graph is a control flow graph corresponding to a program, what can you think of node coverage and edge coverage? Put together, they basically mean you execute every statement in the program, right? Because they insist that you visit every node, and then they insist that you visit every edge. If you write a set of test paths that satisfy this, then you're writing a test path that basically execute every statement in the program. So you're looking for a set of test cases that will exercise or test every statement in the program. Node coverage and edge coverage might be quite difficult to achieve, because for large pieces of program where the control flow graph is fairly large, writing a set of test cases that will achieve execution of every statement, every node or every edge can be a large set of test cases and sometimes infeasible also. So we look at other set of test cases. The next set of structural coverage criteria that I would like to talk about is what is called edge pair coverage. So as the name says, the test requirement here is that you consider pairs of edges, not pairs of edges that are far away from each other, pairs of edges that are consecutive to each other. In other words, you consider paths of length up to 2, right? Paths of length up to 2 includes paths of length 0, which includes nodes, paths of length 1, which are edges, and paths of length 2, which are actually sets of edges that occur one after the other. So if you take this example graph, how many paths of length 2 are there? All these 6 paths are paths of length 2, right? So I start from 1, which is an initial vertex. 5 and 6 are final vertices. So I go from 1 to 4, 4 to 5. Here's a path of length 2, a pair of edges. Then I go from 1 to 4, 4 to 6, another pair of edges that are consecutive. 2, 4, 5, another pair of edges. 2, 4, 6, 3, 4, 5, 3, 4, 6. So my test requirement says you visit all these paths of length 2 exactly once, right? So here they have written length up to 2, but I have listed here paths of length 2. I implicitly assume that it includes paths of length 1 and paths of length 0. So how many test requirements can I write? If you look at this structure of the graph, it so happens that I need one path for meeting each of these TRs, right? I can't do better. So test paths are basically all these 6 things again. I can't write anything shorter. Now, why do I need paths of length up to 2? The same reason we said when we do edge coverage, even though edge is a path of length 1, we changed it as path of length up to 1 because we wanted edge coverage to subsume node coverage. So for the same reason, we want edge pair coverage to subsume node coverage and edge coverage. So we insist that the TR contains all paths of length up to 2. Right? Suppose you're not very particular about this requirement. There is no harm in saying that edge pair coverage means you visit all paths of length exactly 2. Right? So now before we move on, what do you think edge pair coverage would be useful for? Right? One good use of edge pair coverage is to cover all branches in the program. So if you think of this as the control flow graph representing some piece of code, right? Let's not worry about what that piece of code is, but let's assume that this is the CFG for some code. What could node 4 be? Node 4 could be corresponding to an if statement, right? Which says it has 2 branches. If it's then is true, maybe you go to 5. If else is true, maybe you go to 6, right? You do something here, you do something here. So when I do edge pair coverage, what I cover is from 1, 2 and 3. What are the various ways in which I can visit 4? And from 4, what are the various ways in which I can cover the 2 branches that go out of 4? So edge pair coverage is useful. Suppose I think about it. What did I do? I did parts of length 0, which was vertices, node coverage. Then I did parts of length 1, which were edges, edge coverage. Now I say parts of length up to 2, I did edge pair coverage. You can move on, right? You can say parts of length 3, parts of length 4, parts of length 5. Then if we go on like this, what we have is what is called complete path coverage. You have a test requirement, TR, which says that you cover all paths in the graph. Now, if you think about it, what would be the use of this? Will it be useful? What would all paths mean, right? If I say cover all paths in the graph, let's assume a case where the graph has a loop, right? In the 2 examples that we saw in the previous 2 slides, the graphs didn't have a loop, but let's assume that the graph has a loop. How many paths do you think will be there in the graph? There will be infinite number of paths in the graph, right? Because I visit the loop once, I get one path. I visit the loop once again, I get another path. I visit a loop once again, I get another path. So I can go around the loop again and again and again and get more and more paths, longer and longer paths, right? So there will be infinite number of paths. And given these infinite numbers of paths, how do I achieve complete path coverage? I'll have to be able to go on writing test paths, right? So for this reason, complete path coverage is believed to be an infeasible test requirement. Infeasible in the sense that I will never be able to stop testing if I want to achieve complete path coverage intuitively, right? Also, if you think about it, not only is it infeasible, what is the use of it? It may not be very useful for us, right? What's the point in going on repeatedly executing a loop once, twice, thrice, 4 times, and so on, right? It's not interesting, infeasible, and not very useful. So what we say is that we will list complete path coverage as a test requirement, but it's not practically usable. What is practically usable is what is specified path coverage. What is specified path coverage says? It says that the user as a tester, as a test engineer, will give you a set of paths to cover. Your TR will be a set of paths that is specified by a test engineer or a user, which says you cover these paths, right? So paths could be some special things. We don't know what they are, but the tester basically gives a set of paths and says, this is your test requirement. Please write a set of test cases that will cover this path. So we say specified path coverage. Your test requirements contain a set of paths where that set is specified by the user. So we'll go and now move on and see what is one specific useful specified path coverage. Before that, I'll give you another example just to recap all the coverage criteria that we've seen so far. Right? So what are the 4 structural coverage criteria that we saw so far? We saw node coverage, edge pair coverage, and complete path coverage. So let's take a small graph. Here is a graph on the left hand side. It has about 7 nodes. The node 1 is the initial node. There is one final node, which is node 7. If you see, this could constitute a reasonably interesting control flow graph, right? So if you try to map it to assume that it's a control flow graph corresponding to some code, there is branching at statement 1. So maybe there was an if statement here. There is another branching at statement 3. There is another branching at statement 5. One branching ends in the final state 7. One branching goes into a loop between 5 and 6. So maybe there was a while statement here. This means skipping the loop, and this means executing the loop, right? So what will node coverage on such a graph be? Node coverage on such a graph, the test requirement says there are 7 nodes. Please visit all 7 nodes. Right? How many test paths will visit all these 7 nodes? So there could be one test path like this. I do 1, 2, 3, 4, 7. Right? This is a path. This is a test path from the initial node 1 to the final node 7. So in this test paths, I have visited how many nodes? I have visited 5 of my 7 nodes. I have visited nodes 1, 2, 3, 4, and 7. What are the nodes that are left behind? 5 and 6. So I have to write another test path which includes that. So again, because it's a test path, I have to begin from an initial state and end in a final state. So I begin at node 1, then I go to 3. I don't want to go to 4 because I've already considered that in my test path. From 3, I go to 5. And then I don't want to go to 7 because if I do that, then I'll miss visiting node 6. So from 5, I visit node 6. And remember, it's a test path, so I have to be able to end in a final state. So I come back to 5 and then I do 7. right? So that's this test path. So just to summarize, node coverage test requirement says you visit all the 7 nodes, which is the set. And what are the test paths that will visit all the 7 nodes? There are 2 test paths, one which goes like this, 1, 2, 3, 4, 7, which leaves out nodes 5 and 6. So I put another test path which says 1, 3, 5, 6, 5, 7. So these 2 test paths put together satisfy this test requirement of node coverage. Similarly, on this graph, how do I do edge coverage? How many edges are there? So many edges are there, right? 1, 2, 1, 3, 2, 3, 3, 4, 4, 7, and so on, right? So test requirement says you visit all these edges, which is the set of all edges in the graph. What are the 2 test paths? They're very similar to node coverage because I told you, right? Edge coverage is also meant to subsume node coverage. So if I do this test path, 1, 2, 3, 4, 7, I visited all the edges that occur on this side. Now I write another test path that covers the missing edges, which is this 1, 3, 3, 5, 5, 6, 6, 5, and 5, 7. So between these, I have done edge coverage. The next test requirement is edge pair coverage. Edge pair coverage lists all paths of length 2, which is 1, 2, 3, 1, 3, 4, 1, 3, 5, and so on. I've put these dot 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 because I ran out of space to list all the edge pairs, but you can finish this. It's only a finite set, slightly larger than edge set. That's my TR. It says please write paths that will visit all these paths of length 2. That will means it will visit all these consecutive pairs of edges. So test paths for these would be, if you see 1, 2, 3, 4, 7, it covers edge pairs that occur along this path. And then I do 1, 2, 3, 4. I forgot this pair, right? So 2, 3, 3, 5. So I do 3, 5, 7, which covers all test paths along these lines. And then I do 1, 3, 4, 7, which includes this edge pair. Now I have to include 1, 3, 5, 6, 5, 7, which completes all the edge pairs that I had. So with just these 4 test paths, I can achieve the test requirement for edge pair coverage. Now complete path coverage for this graph, please remember this graph has a loop here from 5 to 6. So complete path coverage for this graph, the test requirement will not stop. It will go on listing paths, right? Because I have this path which skips the loop. I have this path which also skips the loop. But then I have to take this path which enters the loop. Once I enters the loop, I have a path that looks like this, which visits the loop once. Then I can do the same thing again. 1, 3, 5, 6, 5, 6, 5, 6, 7. And then I can do 1, 3, 5, 6, 5, 6, 5, 6, 5, 6, 7. And I can go on writing, right? So test requirement for complete path coverage for this graph with a loop will be an infinite set. So obviously I'm not going to be able to make it feasible or write a test path, set of test paths that will execute complete path coverage. It's only for completeness. We really don't consider it as a useful coverage criteria by any means, right? So now we'll see how to overcome this problem about complete path coverage. I have this graph with loops, right? The only way I've touched upon this loop is to be able to do complete path coverage. But then that's not very useful because it gives rise to an infinite number of paths, right? So is there a midway solution, right? So the question that we want to ask is what will be a good notion of specified path coverage in the presence of loops? Now let's look at loops. Assuming that this kind of control flow comes from a loop, when we want to test a loop, what do we ideally want to test? We say that loops have boundary conditions and then they have normal operations. So when I test a loop, maybe I want to test around its boundary condition. And let's say the loop is meant to execute 100 times. It's a for loop for I is equal to 1 to 100. So I don't want to really execute 100 normal executions of the loop, right? So I want to be able to test the loop for its normal execution maybe once. And then I want to be able to test the loop around its boundary conditions. What happens when the loop begins? What happens when the loop ends, right? So when we say we need a set of test cases that cover a loop, we are looking for the following kind of test cases. We execute the loop at its boundary conditions, which will involve skipping the loop also. And then we execute the loop maybe once or a few number of times for its normal operations, right? So the notion of prime paths and prime path coverage help you to achieve this kind of execution for loops. So what are prime paths? Before we look at prime paths, I need to tell you what a simple path is. So what is a simple path? A path from a particular node Ni to another node Nj is said to be simple if no node appears more than once except possibly the first and the last node. So simple paths could be cycles, they could begin and end in the same node. Ni and Nj could be the same vertex, but in between the path, nothing appears more than once, which means there are no internal loops in the graph and every loop is believed to be a simple path. Now moving on, what is a prime path? A prime path is a simple path that does not appear as a subpath of any other simple path. So just to repeat, what is a prime path? It's a simple path. And what is the second condition? Second condition says that it's a simple path that doesn't come as a subpath of any other path. So I'll show you an example to make this definition clear. Let's look at this graph. It has 4 nodes, right? 1, 2, 3, 4. How many simple paths are there? If you go and see this listing, what I have done is I have listed all the simple paths. I've listed them in a particular order, in fact. Maybe we'll begin at this end, right? This 1, 2, 3, 4, if you see right at the end of the list of simple paths, they are simple paths of length 1. Later, we've moved ahead and listed simple paths of length 2, which are basically, 1, 2, 3, 4 are simple paths of length 0. They just contain single vertices. Then I have gone ahead and listed simple paths of length 1, which are just edges. Then here I have listed simple paths of length 2, which are edge pairs like thing. And then I have listed simple paths of length 3. The other thing to note is that this is a graph with 4 vertices. So simple path means no vertex should be repeated. So if I have that condition, then what is the maximal length simple path that I can have with 4 vertices? The maximal length simple path that I can have with 4 vertices should be of length 3, right? Because the moment I increase one more edge, I'm repeating one vertex, right? So the maximum length that I can get without repeating a vertex with 4 vertices is of length 3, right? So now if you look at all these simple paths, there's so many of them, I say out of all these simple paths, only these are prime paths. Why do I say these are prime paths? Go back to the definition of prime path. Prime path should be simple. Prime path should not be a subpath of any other path, right? So if you take a path that looks like this, let's take 4, 1, 2, this path, right? 4, 1, 2. If I take a path like that, this 4, 1, 2 path comes as a subpath of this path here, 2, 4, 1, 2. It also comes as a subpath of this path here, 3, 4, 1, 2. So 4, 1, 2 doesn't qualify to be a prime path. Similarly, if I take something like 2, 4. 2, 4 occurs as a subpath here, 1, 2, 4. It occurs as a subpath here, 2, 4, 1. It occurs as a subpath here, 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 several places. So a path like 2, 4 doesn't qualify to be a prime path. If I go on looking like this, I basically eliminate all paths of length 0, 1, 2, and 3. And only paths of length 4, in this case, happen to be prime paths because none of these paths of length 4 occur as subpaths of each other. Right? So this graph has several simple paths, but it has only about 8 prime paths. Right? Now, what is prime path coverage? Prime path coverage, very simple. The test requirement for prime path coverage says, please cover all the prime paths in G. Right? So now, to be able to meet this test requirement, you need to write a set of test paths that first identify the prime paths in C and then cover them. So in the next lecture, I'll tell you how to do this. What are the algorithms that will do this? But for now, we'll go ahead and see a little bit more about prime paths coverage without worrying about how to do it. So the first thing that I want to tell you is that prime path coverage actually meets this loop coverage criteria that I told you about, right? This one. Test a loop at its boundary and test a loop for its normal operations. So we'll understand how that happens. Prime path coverage ensures that loops are skipped and executed, and it towards all paths of length 0 and 1. We saw that for that example at least. So by default, it subsumes node and edge coverage, right? Because if you see here, it includes node coverage and it includes edge coverage. This note says that it may or may not subsume edge pair coverage. Why is that so? I'll show you an example. Consider a graph that looks like this. It has 3 vertices and then it's got a self loop here, right? So edge pair coverage for this graph requires that this self loop needs to be visited. So edge pair coverage for this graph will say you visit this edge 1, 2, 2. You visit this path of length 2, which is 1 to 2 and 2 to itself. But if you look at this path 1, 2, 2, if you see the vertex 2 repeats here, right? And that violates the condition of it being a prime path. Remember, prime paths are simple paths. No intermediate vertices are supposed to repeat. They're not supposed to have loops. So except for this problem, prime path coverage does cover edge pair coverage, but not for graphs like this. If a graph looks like this, right, prime path coverage does cover edge pair coverage. But if a graph has a self loop, then prime path coverage does not cover edge pair coverage. Right? So now we'll move on and understand how prime paths cover the notion of a loop. So we'll go back to this example graph that we looked at a few slides earlier. In this example, there is this loop here, right, between nodes 5 and 6. And I'm not listing the prime paths for this graph, but you can take it on faith that this graph has 9 prime paths. In the next module, I'll tell you how to list all those 9 prime paths. So then if you see this is one prime path, right? 1, 3, 5, 7, because it's a simple path and it doesn't occur as a subpath of any other path, right? So this prime path for this particular example corresponds to skipping this loop because it completely avoids this loop. And if you see, here is another prime path, 1, 3, 5 and 6. This prime path gets into the loop, it corresponds to executing the loop once. And then this is another prime path for this example, 6, 5, 6. Why is this a prime path? Remember, in prime paths, which are simple paths, the beginning and ending nodes are allowed to repeat. Only the intermediate nodes are not allowed to repeat. So 6, 5, 6 is a prime path. And what is the main job that 6, 5, 6 is doing for this graph? It is executing the loop more than once. So if you see these 3 prime paths, 1, 3, 5, 7 skips the loop, 1, 3, 5, 6 enters the loop, and then 6, 5, 6 helps you to execute the loop for its normal operation. So it is intuitively in this sense that prime paths exactly capture loop coverage the way we want them to do in test case design, right? So one important thing is that how I told you, right, in the next module I tell you how to come up with an algorithm that will help us to design test cases that will meet the test requirement of prime path coverage. But before we do that, I'll tell you we could have some problems. Like for example, you take a graph like this, right? Prime path coverage for this graph, this is a prime path, 1, 2, 3, 4, 5. This is a prime path, right? It might so happen this graph, if this graph corresponds to the control flow graph of some piece of code, here is a loop. It might so happen that this code from which this control flow graph is derived, the loop present at statement number 3 and 6 is such that you can never write, you have to execute the loop at least once. Like for example, if I take a C program, right, there are 2 kinds of loops. There is a do while and a while do loop, right? While for a while do loop first checks the condition and then executes the loop. But if I have a do while loop, I have to execute the loop at least once before I move on. So it might be an infeasible test requirement for that kind of a code when I say that you achieve this prime path without executing the loop. Why should I not execute the loop? Because if I execute the loop, then the vertex 3, which is an intermediate vertex in this path, will occur more than once. So it will not be a prime path, right? So 1, 2, 3, 6, 3, 4, 5 is not a prime path because 3 occurs more than once. 1, 2, 3, 4, 5 is a prime path. But to be able to write a test path and execute it in the code to achieve 1, 2, 3, 4, 5, the code might be such that I might have to go through this loop once, like I told you, right? The code might have a do while statement. So how do we get over this? We get over this by using a notion of a side trip and a detour, right? So we'll see what they are. So what is a tour? Tour I introduced to you in the last module when we looked at graphs. Tour is a test path that tours a subpath if Q is a subpath of the overall test path. So what is a tour with a side trip? A tour with a side trip is the following. A test path P tours a subpath Q with side trips if every edge of Q is also in P in the same order. It's like taking a side trip as a part of your main holiday, right? And what is a tour with a detour? A tour with a detour is a test path P tours a subpath Q with a detour if edges don't come in the same order, but vertices come in the same order, right? So I'll show you an example. So here is my test path 1, 2, 3, 4, 5. I take the same test path to meet the prime path coverage of 1, 2, 3, 4, 5 with the side trip. So what do I do in the side trip? Side trip says that it's the same path 1, 2, 3, 4, 5, but I do 1, 2, 3, take a side trip around 6, come back to 3 and do 4, 5. So I retain the vertices that come in the main path. See, side trip says that you retain vertices that come in the same path in the same order. I retain the vertices 1, 2, 3, 6, 3, 4, 5. But in the main path, which is this blue dotted line, the vertices occur in the same order, right? Now, what is a detour? Detour says you retain the edges in the same order, may or may not retain vertices in the same order. So a detour looks like this: 1, 2, 3, 6, 4, 5. Right? It's left this edge. It doesn't retain edges in the same order, but it retains this path. Right? So why do I need this? I need this because to be able to achieve this prime path coverage, I might have to go through the loop. And if I go through the loop, the prime path ceases to be a prime path. So I do a small workaround and say I actually cover this prime path, but with the help of a side trip. Sometimes I might say I cover this prime path, but with the help of a detour. They are just extra additions that we add so as to not to alter the notion of prime paths being simple paths. But I still want to be able to achieve these test requirements, right? So this is what I was telling you about. Some test requirements related to graph coverage criteria may be infeasible. In fact, it's undecidable to check whether even a test requirement is feasible or not. We won't really go into those details. But typically, when I allow side trips, then I might be able to achieve test requirements with reference to a particular code. So what is called a best effort turing is that you try to satisfy as many test requirements as possible without side trips or detours. And then if you still have test requirements that are unachievable, consider using side trips and detours to be able to satisfy them, right? So what is a round trip? A round trip is a prime path that starts and ends in the same node. We've seen these. These are just specific kinds of prime path. What is a simple round trip coverage? Test requirement contains one round trip path for each reachable node that begins and ends in the same vertex. What is complete round trip coverage? Test requirement contains all the round trip paths, right? So they subsume edge and node. They do not subsume edge pair, edge or node coverage, right? Now to summarize, what are the various coverage criteria we saw? We saw node coverage, visit every node; edge coverage, visit every edge; edge pair coverage, visit every path of length at most 2; visit prime paths means compute all the prime paths, write test paths that exactly visit every prime paths. We'll see how to do this in the next module. Then complete path coverage, which means visit every path in the graph, which is, I believe, a useless test requirement. And then we had these two, which talk about round trips. They are basically prime paths, but begin and end in the same node. And why have I put them in the structure? This structure captures how each of them subsume the other. We discussed this, right? Edge coverage subsumes node coverage. Edge pair coverage subsumes both edge coverage and node coverage. Prime path coverage, except for graphs with self loops, subsume edge pair coverage, edge coverage and node coverage. Complete path coverage subsumes everything but is infeasible and useless. So what we will see in the next module is how do we look at algorithms that, given each of these structural coverage test requirements, how do I come up with test cases? Edge pair and node coverage are easy to do, but prime path coverage is a nice algorithm. So we'll spend most of the next module looking at these algorithms. Thank you.